Good morning, friends. Today we are going to learn about square well potential with finite walls. In the previous class, we already have an idea of how the problem of particle in a box or a particle trapped in an infinite square well potential is analyzed. So we have considered the potential of the particle trapped in a box as a 0, and outside the box or a infinite square well potential well, the potential is infinity. That is actually how the problem is dealt with by imposing a boundary condition, box normalization condition for a free particle. Okay, so we already have the wave function or Eigen function obtained and the corresponding Eigen values. Now our aim is to analyze the square well potential with finite walls. So when I say this square well potential with the finite walls, we have to think that the potential considered is not of infinite height but of finite one. So this is the potential considered. This is the height. So I'll take it as V0, and the region, the dimension is in one dimension we are considering. This is from -a to 0 to plus a. Okay, this is towards minus infinity, and here we have plus infinity. Okay, so this is the positive x-axis and this is the negative x-axis. So this is the situation. Now we have to consider a particle in this box. Okay, so when we say that a particle is confined in a square well potential with finite walls, we have to analyze various factors about the amount of energy the particle have. Also, it has a boundary of finite walls. So if we write the potential at various regions of X, so let us name this region as region 1, region 2, and this is region 3. So if we divide the available space into 3 regions and write the value of potential, V of X is equal to V0 for x less than minus a and 0 for minus a less than x less than capital A, yeah, okay, and V0 again for x greater than plus a. So this is the situation. This is the case of variation of potential in 3 different regions. So this is actually region 1, this is region 2, and this is region 3. Okay, now we have an idea about the amount of barrier the particle has to face. Now, we have a clear idea about the regions, possibility of movement of the particle. Now, let us find the Schrodinger equation in various regions. So, let us take the second region because it is easy for us since we have just completed the case of particle in a box. So let us go for region 2. So in region 2, as we know, there is no potential. So let us write the Schrodinger equation. The Schrodinger equation is d square psi by dx square plus k square psi is equal to 0. That means the particle uh, is a free particle within this finite well. Uh, yeah, yes. So as you remember the value of k square is equal to 2me by h cut square. Okay. Now, once we have this kind of equation, the possible solution is, as we have considered in the case of particle in a box, we have psi of x is equal to a sine kx plus b cos kx. Okay, so this is the situation in region 2. Sorry. Now we have to analyze region 1 and 2. I mean 1 and 3. 1 and 3 is almost the behavior of particle in 1 and 3 may look like the same. So because both are a finite wall of or a finite barrier of height v0. So let us say 1 and 3. For region 1 and 3, we shall include the value of potential in the Schrodinger equation. So minus h cut square by 2m d square psi by dx square plus v0 psi is equal to E psi. So if you remember, we have used the same equation and applied v0 is equal to 0 and rearranged by multiplying 2m by minus h cut square to the right hand side and apply the value of k square here. Okay, so in region 1 and 3 we have v0 also. So that is our Schrodinger equation. Now let us go for the possible solutions. So if we have to consider the solutions, first let us take the availability of the particle's energy. So particle is having an energy say E less than V0. There are two possibilities, either E less than V0 or E greater than V0. But the normal thing is that E less than V0. Okay, there is no chance for the particle to attain an energy E greater than V0. If by any means it acquires some energy, then we can consider this case. So our first consideration is for E less than V0. Okay. So okay, we will analyze the case. if the particle is having very small energy, this means that it cannot move or cross region 1 and 3. So we can say that the particle is confined. The particle is confined if the energy is less than V0. The particle will be confined in region 2. Okay. The most probability of the particle to be in this region is going to be a maximum in the center region of the wall. I mean well. Okay. So there is going to be a very small probability for the particle to penetrate through the walls. Okay. So we can say that the particle is confined and it is a bound state problem. So since there is a chance for the particle to be in the region, most probably we can say that it is a bound state problem. Okay. So let us analyze the Schrodinger equation once more. By rearranging, we can have our equation is minus h cut square by 2m d square psi by dx square plus v0 psi is equal to e psi. Let us rearrange by dividing throughout by minus 2m by h cut square. So you will have d square psi by dx square plus minus 2m v0 by h cut square psi is equal to minus 2m e by h cut square psi. Now let us combine these two equations, these two terms. So we will have d square psi by dx square, and let us take a minus outside. So once this term comes to the left hand side, it will be positive, but when I take minus outside, that will be minus within the brackets. So it is 2m by h cut square. If you want, you can remove this bracket because 2m by h cut square is a common term, and v0 minus e into psi is equal to 0. So this is our equation in region 1 and 3. Okay, now let us take a possible solution. So before that, let us assume two constants, that is 2m. We already have a term k square, right? 2m e by h cut square. So let us give this value 2m by h cut square v0 minus e as alpha square. So rewriting this one, d square psi by dx square minus alpha square psi is equal to 0. So this is the modified version of our Schrodinger equation in the case when the particle having energy less than the potential. Okay. Now the possible solution. Let us consider the possible solution, that is psi of x. Psi of x is equal to c e raised to minus alpha x plus d e raised to alpha x. So let us consider this one as the possible solution to this equation. And now our task is to analyze the possible values of these two terms. As you know, in the case of finite square well potential, okay, finite square well potential, we have this is the situation. Yeah, this one. So in this case, you have to think how the values of these two terms varies. Here you have minus infinity, and here it will be plus infinity as we move forward. So e raised to c e raised to minus alpha x is going to take two different values. That is c e raised to minus alpha into, if x is minus infinity, it is into minus infinity. That means this is going to be c e raised to infinity, because minus and minus becomes plus, so this is going to be infinity. Now second term, d e raised to alpha into minus infinity. That means it is d e raised to minus infinity, that is going to be 0. That means this term helps the wave function to be converging in region 1. So we have to retain this term in region 1. Okay. The other one is diverging value. So we need not consider this one, because the wave function is something that says about the particle to be present in the considered region. So if the wave function is increasing, we cannot say that the particle is possibly there. So we have to consider a finite value or a decreasing value of a wave function in that region. So for region 1, this is the relevant term. And likewise for the region 3. For region 3, you will have similar terms, and when you apply plus infinity, this term, the first term, will be of relevance, because that is the one getting decreased. Okay. So for region 3, you will have c e raised to minus alpha x is the one which is confined. So this is the these are the two values to be considered in region 1 and 3. Okay. So I hope you understood, because we need a wave function is something that represents the particle to be present somewhere in that region. If it is going to be an increasing function, which is clear, which makes clear that the way there is no possibility of the wave particle to be present there. Okay, and there is a chance of the particle to escape from that region. So we need a finite value so that we can locate the particle somewhere in that region. So these two terms, this term d e raised to minus alpha x in region 1 and c e raised to minus alpha x in region 3 gives a finite value or a smaller decreasing value. That means we can choose these two as the corresponding wave functions in 1 and 3. Okay, so in this case, let us write the value of a wave function. Yeah, let me use a different color. Okay, so wave function psi of x is equal to d e raised to minus alpha x for region 1, and we already have in region 2 we already have a sin kx plus b cos kx, so we need not worry about that. That is already a bound state case, so that is region 2. And we have c e raised to minus alpha x in region 3. So these two are the possible values of wave functions in 3 different regions. Okay, now let us analyze how these wave functions behave according to the properties of wave functions. So we have to think about the symmetry property of the wave function. The symmetry property and the continuity. The continuity property of the wave function is satisfied, then we can say that this is a most suitable wave function. So we have, yeah. Yeah, the continuity property is that here you have minus a, here you have plus a. So the wave function in region 1 and 2 at minus a should be equal, and also wave function at the boundary plus a in region 2 and region 3 should be equal, and that is what meant by continuity condition of wave function. So continuity property should be satisfied in the case of the derivative of wave function as well. So let us consider if the wave function is symmetric. So for symmetric case, if we take symmetric case, you have to take the cosine function, because in region 2 we have to retain only cosine function, because this is a symmetric function and this is a anti-symmetric function. Okay, so in at x is equal to minus a, applying x equal to minus a at in region 1 and 2, that is at the boundary. So we have d e raised to minus alpha into minus a should be equal to b cos k into minus a, and also its derivative. We take derivative d by dA, d into alpha into e raised to alpha a, you have both minus, it will be a positive term, is equal to, the derivative is b cos of minus k is cos ka itself, so you have b k into sin ka. Now the second case, that is at x is equal to plus a, the at x equal to plus a means you have to consider the boundary of region 2 and 3. So in region 2 you have a sin kx, sorry, cos ka is equal to c e raised to minus alpha a, and the derivative is a k sine ka is equal to minus c alpha e raised to minus alpha a. Okay, alpha x, not minus, so I should correct it here. It is d e raised to alpha x, c e raised to minus alpha x, and d e raised to alpha x. So the mistake comes below also. Yeah, here it is actually positive. This one here it is actually positive, so it will be minus, and the derivative also will have a minus alpha. Okay, now it is correct. So you have the term d e raised to d alpha e raised to minus alpha a is equal to b cos ka, and the derivative you have d alpha e raised to minus alpha a, and bk, yeah, minus is cancelled, bk sine ka. Okay, now it is correct. Now if you divide either of these, this one, for example, if I divide this one, that is d alpha e raised to minus alpha a divided by d e raised to minus alpha a, and the right hand side b k sine ka divided by b cos ka. So you can see that yeah, this get cancelled. Alpha will be the only remaining term, and here also b will be cancelled. So this is alpha is equal to k tan ka. If you multiply it with a, both the sides, you have alpha a is equal to ka tan ka. Okay, so this is the case of a symmetric wave function. If the wave function is symmetric, yeah. If it is anti-symmetric, also you will have another set of equations. This is the symmetric case. Now if the anti-symmetric case is considered, you will have a sine function instead of cosine. So doing the same steps at x equal to minus a and x equal to plus a, that is the boundary of region 1 and 2 and 2 and 3, the continuity condition to be satisfied. So you will have equations like this: anti-symmetric, at x equal to, sorry, okay. So if I show the symmetric case also, you can compare. That is what I am doing. So at x equal to minus a, you will have the terms, yeah, d d e raised to minus alpha a is equal to a sine ka. Yeah, minus of a sine ka, because we are applying minus a here. Okay, and the derivative part is d minus alpha e raised to minus alpha a is equal to minus a cos, yeah, a k cos ka, and at x equal to plus a also you will have b, sorry, no, a sine ka is equal to c e raised to minus alpha a. Yeah, the derivative is yeah, we are applying plus a here. The derivative is a k cos ka sine, okay, cos ka is equal to minus c alpha e raised to minus alpha a. Okay, so again dividing, you will have dividing the second equation with the first one, any of this, either of the boundary, the values at x equal to plus a or x equal to minus a. So you, what you're going to get is ka cot ka is equal to minus alpha a. So you have two equations now. This is the case when the wave function is anti-symmetric, and this is the case where the wave function is symmetric. This is for symmetric, and this is the anti-symmetric case. Yeah, because second equation you have a cosine, and the first equation you have sine, you will have cot ka, and like the same steps as the above symmetric case, you will have a k, then alpha, then we have multiplied with the a, so you have this one. The only difference is that you have a minus here in the case of anti-symmetric case. Okay, now what we are going to do with these two equations. Now next task is to analyze these two equations, and let us just take the value of ka is equal to beta, yeah, let ka is equal to beta and alpha a is equal to gamma. So you will have gamma is equal to beta tan beta, also minus gamma is equal to beta cot beta. By giving these two values, you have from the above two equations, from the symmetric and anti-symmetric case, you will have these two equations. Now squaring, you can have beta square is equal to, yeah, these two equations, squaring these two equations, you have beta square is equal to k square a square. K square is actually, k square is 2m e by h cut square into a square, and also gamma square. Gamma square is alpha square a square you know that alpha is 2, sorry, alpha is 2m v0 minus e divided by h cut square into a square. So adding these two, beta square plus gamma square is equal to in both you have 2m e a square by h cut square. So this is 2m, yeah, this is minus e, the term with e is minus 2m e a square by h cut square plus 2m v0 a square by h cut square. Okay. So cancelling these two, you have 2m v0 a square by h cut square. This look like an equation to a circle of radius square root of this one. This is actually a square plus b square is equal to 1. Okay, so instead of that you have a constant. So this is going to be the radius of the circle. So let us plot it in beta gamma plane. Okay, so plotting this circle and these two equations in beta gamma plane. So let us check how it is going to look like. Plotting these equations. Yeah. This is beta is equal to Ka, and on the y-axis you have gamma is equal to alpha A. Okay, let the values vary, like 0, pi by 2, pi, then 3 pi by 2, etc. That means pi by 2 corresponds to this line, pi corresponds to this line, 3 pi by 2 corresponds to this line. Okay, and our circle is going to be, yeah, the curves of beta tan beta and beta cot beta is going to be like this. And the circle, corresponding circles will be like this. Okay, like this. The first line represents this one represents K, yeah, beta tan beta, gamma is equal to beta tan beta, and this one beta cot beta, and alternately like that, minus gamma is equal to, okay. if you analyze the intersection of curves beta tan beta is equal to gamma and beta cot beta is equal to minus gamma. So the first circle will have an intersection of one number, and the second circle is having an intersection of 2, and that increases like that. It increases like 1, 2, 3, then 4, like that. Okay, this means that for beta tan beta is equal to gamma, you will have corresponding values of the odd numbers of the integer n. If we consider the energy values, actually our equation is beta square is equal to, you already have beta square is equal to k square a square is equal to 2m e a square by h cut square. Okay, so if we give suffix n, the quantum number n, you have en is equal to h cut square k square a square by 2m a square, and if you apply ka is equal to beta n suffix, so it is h cut square beta n square by 2m a square. For n is equal to 1, 3, 5, etc., you have energy values E1, E3, E5. You will get correspondingly for beta 1, beta 3, etc. That is, when the odd values of beta, you have energy values E1, E3, E5, etc. And that is obtained from, these odd values are obtained from beta cot beta is equal to minus gamma. And the even terms, this is what we understand. The even terms are, that is for n equal to 2, 4, etc. are obtained, and the corresponding energy values are from beta tan beta is equal to gamma. So this is what we understand. So what is the conclusion of this analysis? So we have a single intersection in the case of a circle with radius between 0 and pi by 2. 0 less than radius less than pi by 2. So you have single intersection. But when the radius is between pi by 2 and pi, you have two intersections, and it goes like that. This means one intersection corresponds to first energy level. That is the symmetric case. First intersection corresponds to the first energy level, and that is a symmetric case. Okay, so that means 0 less than radius less than pi by 2. Let us analyze that. Let us just analyze the radius. This is the radius, right? So 0, one intersection is obtained for 0 less than radius. Radius is 2m b0 a square by h cut square less than pi by 2. Okay, so the maximum radius is 2m v0 a square by h cut square is equal to pi by 2. Okay, that means v0 a square is equal to h cut square pi by 2 divided by 2m. Yeah, radius means the square root of this. That means it should be squared. Pi square 2 square. Okay. So v0 a square is pi square h cut square by 8m. And for two intersections, for the second case, it should be pi square instead of pi. So this analysis indicates that what we are getting from the values is the corresponding energy values. So what we have obtained is the possible energy values. And for the second case, for the two intersection case, if you equate 2m v0 a square by h cut square to pi square, you will have energy in the case of first excited state, and it goes like that. So the value of v0 a square, based on v0 a square, you can analyze the energy, the possible energies and the wave functions. We already have an idea of how the wave function varies in three different regions. So let us plot it. Yeah, if you plot it, for the ground state, so let me give this one as n is equal to 1. N is equal to 1. So when I plot the wave function, what I get is a penetrating value of wave function, because as you know, e raised to minus infinity, as it approaches infinity, it becomes 0. Otherwise, there is a tail penetrating to region 1 and 3. And for n is equal to 2, you can see that yeah. Yeah, yet the anti-symmetric. Yeah, you can see for n is equal to 1, you can see for n is equal to 1, you have an increasing value of wave function and reaches maximum at the center, and you have tails on both the regions. That means the probability is not going to zero abruptly. There is a chance of penetration because of this non-zero value of probability here. And for n is equal to 2, you have, yeah, should be symmetric like this. Okay. So in all the cases, you have a value of wave function getting penetrated into region 1 and 3. This is 2. And if we draw n equal to 2 case, 3 case, that also will show the height of my wall is not sufficient to draw n is equal to 3, so I am not going to try that. And the shape is going to be, yeah, I'll draw this one, and it will look like this for n is equal to 3. So it should not go beyond the wall. Okay, so that is how the probability varies. So all these represented n equal to 1, 2, 3 are bound states. And we have also seen that the wave functions have tails beyond the classical turning points. This means that there is a finite probability for the particle to be outside this well. This means quantum mechanically there is a chance for the particle to tunnel or leak into the classically forbidden regions. Okay, this is how we analyze the case of energy less than V0, and this is how we obtain the values of a wave function and the energy values from the plot of beta tan beta is equal to gamma and beta cot beta is equal to minus gamma. So we have obtained the possible energy eigenvalues as well. I hope you understood. I'll just give you a quick recap of what we have done. First of all, we have analyzed the situation by drawing the well. See, you can see it here. We have three different regions. In the second region, you have a V0 equal to 0. That is between minus A to plus A. In 1 and 3, you have potential V0. So we wrote the value of potential in three different regions like this. And we also wrote the value of Schrodinger equation in various regions, and from region 2 you have V0 equal to 0. So as this situation is the same like a particle in a box, so you have the constant k square is equal to 2m e by h cut square, and the possible wave function is this one. And in 1 and 3 the condition is the same, so we take the same kind of Schrodinger equation by applying V0. Now you have to think whether the particle is having sufficient energy. So first of all, we have to consider the case where E less than V0. There is also a possibility of energy of the particle greater than the barrier V0. So if energy is less than V0, it is considered as a bound state, or the particle is going to be confined within that potential barrier. So we have rearranged Schrodinger equation and we have alpha square, so that the equation turns out to be like this. and we have checked the value of wave function, the properties of wave function, like continuity property of the wave function and its derivative. So we understood that in region 1 you will have d e raised to minus alpha x, sorry, d e raised to plus alpha x, and in region 3 you will have c e raised to minus alpha x, so that you have a well-defined wave function, decreasing value of wave function, so that the particle is a bound in a bound state, or confined in the specified region 2. So you have wave functions like this. Since you have a sine kx and b cos kx, you have to check the symmetric and anti-symmetric case. So analyzing the symmetric and anti-symmetric case by applying the continuity condition at both the boundaries x equal to minus a and x equal to plus a, you have two equations. The symmetric case, you have alpha a is equal to ka tan ka, and for anti-symmetric case you have ka cot ka is equal to minus alpha a. So yeah, again modifying those as ka is equal to beta and alpha equal to gamma, you have two equations in terms of beta and gamma. And taking the values of beta and gamma, we have another equation for a circle. So we have plotted the circle and these two equations, beta tan beta equal to gamma and beta cot beta equal to minus gamma. So we have a specific pattern obtained, and analyzing that pattern we obtained different values of energy. That is, odd values corresponds to the intersections obtained with the circle and beta cot beta equal to minus gamma, and the even values are obtained from that of beta tan beta is equal to gamma and the circle. So analyzing that, we obtained the variation of V0 A square with the number of intersections increases, so that we have the energy values. And we have also plotted the wave function. So we obtain that even though particle is confined, the wave function, the tail of wave function is extended into region 1 and 3. That means there is a chance of penetration of particle into region 1 and 3, which is possible only quantum mechanically. So this is a case of energy of the particle less than V0. And if the energy of the particle is greater than V0, the quantity of alpha becomes imaginary. That means the solution to our Schrodinger equation, that is h cut square by 2m d square psi by dx square plus V0 psi is equal to E psi, will be sinusoidal in 1 and 3. Okay, so if the solution, the wave function is sinusoidal, that means there is a possibility of a particle extending from 1, 2 and 3. So the case is not a bound state. The particle is not confined. So the chance, we have a probability saying that there is a chance for the particle to be extended in all the regions. So we are, that is not of significance because it is not a bound state. So that's all about the square well potential with the finite walls.